Hello everyone, my name is Avesh Kumar Uprawal. Today we will study Chinese remainder theorem. To make this presentation, I have taken the content from The History of Chinese Remainder Theorem by Law Hong Ying. Law Hong Ying is a faculty of computer and environmental studies at University of Putra, Malaysia. The flow of my presentation will be in history. I will cover where we have found this problem and why it is called Chinese remainder theorem. How the development of Chinese remainder theorem started. Then I will explain about the proof of the Chinese remainder theorem. Then I will take one example. Then the application of the Chinese remainder theorem. Then the one assignment question which will be fun to solve. And the useful link which I have not covered in this video that will help you to enhance your knowledge, and the references which I have used to make this presentation. The remainder problem was first discovered in the 3rd century. It was found in the mathematical treatise entitled Sanjing Zhaojing, of which the author was unknown. Nowadays, the remainder problem of the Sanjing Zhaojing is known as Chinese remainder theorem because it was first appeared in the Chinese mathematical treatise. We have found this problem in the Sanjing Zhaojing in chapter 3, problem number 26, which states that there are unknown number of things. If we count by 3, there is a remainder 2. If we count by 5, there is a remainder 3. If we count by 7, there is a remainder 2. If we count by, then find the number of things. The author of Sanjing Zhaojing does not provide any explanation to the solution, which raised many queries among the researchers who wish to master this theorem completely. Now I will tell you what is the solution provided by the author. In this, author tells that if we count by 3, there is a remainder 2, put down 140. Then if we count by 5, the remainder is 3, put down 63. If we count by 7, the remainder is 2, put down 30. And then obtain 233 and subtract 210 to get the answer. Then the second solution he provided is, if we count by 3, the remainder is 1, put down 70. If we count by 5, the remainder is 1, put down 21. If we count by 7, the remainder is 1, put down 15. When the number exceeds 107, the result is obtained by subtracting 105. Here, he does not explain why you are subtracting 105, why you have taken the number 70, 21 and 15. So, what the Chinese remainder states that let m1, m2, mk be an integer such that mi to mj equals to 1 where I is not equals to j. Then for any integer a1, a2 to ak, the system of equation x is equals to ai mod mi, I is equals to 1 to 2k has a solution. Further, any solution will be congruent mod m1, m2 to mk. Then we have to prove, then for any integer a1, a2 to ak, the system of equation. Now, here I am assuming we have established the proof for k is equals to 2. If you want to study for k is equals 1 and k is equals to 2, you can go into my useful link where in the book they have provided the complete solution. Now I will start with k is equals to 2, assuming that you know the solution. Okay. Then we have to suppose that theorem is true for z1, z2 to zk. What is z1, z2, zk? z1, z2, zk are the relative prime number. Then we have to prove it for k plus 1. Because we are proving it by the metaphor induction, that's why we have to take to prove it for k plus 1. Here x1 is a1 mod m1 to x is equals to ak mod mk. Then we can write it as x is equals to a k plus 1 to mod of m k plus 1, where mi mj is equals to 1 for all I is not equals to j and ai's are arbitrary. By the inductive hypothesis, there is a solution B to the first k congruences says B is equals to A1 mod M1, B is equals to A2 mod M2 to B is equals to AK mod MK. Now consider the system of two congruences. X is equals to A1 mod M1 M2 to MK. Therefore, X is equals to AK mod MK plus 1. Since Mi MK plus 1 is equals to 1 for I is equals to 1, 2 to K, we have M1 M2 MK plus 1. So, the two moduli are relative prime. Hence, we have proved two moduli has a relative prime. Therefore, we have proved this equation of Chinese remainder theorem. Now, I will consider one example based on Chinese remainder theorem. Here, x is equals to 2 mod 3, 3 mod 5 and 2 mod 7. And the z is equals to b1 x1 c1 plus b2 x2 c2 plus b3 x3 c3. The derivation of this formula is provided in the useful link in the textbook. Then what is b1 x1 c1, where c1 is 2, c2 is 3, c3 is 2, b1 is 3, b2 is 5, b3 is 7. To calculate bi, the formula is b1 is equals to b2 into b3. Therefore, we will multiply 5 into 7 to get the answer 35. b2, b1 into b3, b1 is 3, b3 is 7. Now we will multiply 7 into 3, then we will get the answer 21. To calculate b3, we will multiply b1 into b2, which is equals to 3 into 5, then we will get 35. To calculate xi, we will use the formula bi xi is equals to 1 mod bi. Now we will equate the value of bi is 35, which we have calculated earlier. But 1 is not a multiple of 35, so we will first take the 35 mod 3, which is equals to 2. Then we can write it as 2x1 is equals to 1 mod 3. But 1 is not a multiple of 3. But we can add 3 in 1. So 4 mod 3 is equals to 1. So that does not change our equation. So we can add 3 in LHS. So 2 is a multiple of 4. We can divide 4 by 2. So we will get x1 is equals to 2. Now we will put the value of b2, that is 21x2 is equals to 1 mod 5. 21 is also not a multiple of 21. We can further apply the mod operation, that is 21 mod 5 is equals to 1 x2, that is equals to 1 mod 5. Where 1 is a multiple of 1, we can write it as x2 is equals to 1. Now we will substitute the value of b3, that is 15 x3 plus 1 mod 7. Here we have to apply the mod operation of by 7, that is 15 mod 7, which is 1. Therefore 1 x3 is equals to 1 mod 3. 1 is a multiple of 1, we can write it as x3 is equals to 1. Now we will put all these value in the equation z. The equation z is b1 x1 c1 plus b2 x2 c2 plus b3 x3 ct. By substituting all this value, we will get the answer 233. But we can apply the mod operation, it will become 23 mod 105. The value of z is not unique, it can be multiples of b. That is b, how we will calculate b? b is b1 b2 into b3. So 3 into 5 into 7, that is 105. The solution we will get the multiples of 105, which can be minus 187, minus 82, minus 23, 128 and 233. The application. The David-Speiler example of fast parallel arithmetic to justify its algorithm. Here, the David Speiler is used Chinese remainder theorem to justify his algorithm only. It is also used to resolve multiple range ambiguities in many radar systems. What is multiple range ambiguity? The multiple range ambiguity resolution is a technique which is used with medium pulse repetition frequency, that is PRF, radar to obtain range of information from distances that exceeds the distance between transmit pulses, the reflected signal to be folded so that the apparent range is modulo function of the two range. Now the third application, it is used in cryptography in RSA algorithm. In recent paper of RSA, the Chinese remainder theorem is used in the decryption process, which can be solved that RSA algorithm very fastly. Now I will give you one assignment question. You have to solve it. This problem is an ancient Chinese problem. It said that there are a band of 17 pirates who stole a sack of gold coin, where they have tried to divide the fortune into equal portions, but while dividing it, the 3 coins remained. In the ensuring barrel over who should get the extra coin, in that ensuring barrel, one pirate was killed. Then the remaining coin was equally distributed, but still 10 coins were left. Again the argument developed in which another pirate was killed, but now the fortune can be evenly distributed. Now you have to calculate what is the least number of coins which can have been stolen, and the second, what all the possible number of coins which could have been stolen. Useful link. In the first useful link, you will get the basic information about the Chinese remainder theorem. It is a notes by the Stanford University. Second link is a Wikipedia link in which you will get the information, basic information about the Chinese remainder theorem, its history, and etc. Second, third and fourth are the research paper which you will get by this link about the Chinese remainder theorem. And last one is the research paper of the that topic I have told you about, which is now the references. To make this presentation, I have used the two books. First book is History of Mathematics by Victor Kurtz. Second, Elementary Number Theory with Application by Thomas Koshai. And The History of Chinese Remainder Theorem by Law Hong Ying. Thank you.